This is PowerPoint for the second math quiz, and there's some redundancy here. We're going to start with calculation of mass. So the graphic on page 59, I think, is inverted, and it just makes it simpler and easier to keep up with what you're dividing if you put mass on top and MA and time on bottom. So if you're missing a variable, MA times time equals mass, MA divided by or MAS divided by MA gives you time. MAS divided by time gives you MA. So how much time is needed at 350 MA to get 40 mass? The 40 would go on top and you divide that by 350. So what you would have is 40 divided by 350 is equal to X. So X is 0.11. 20 mass is needed, and only the 3/15 station is accurate. First off, if you're using a 3/15 station, you're probably using a single-phase generator, probably full wave rectified, and you might not see those very often. Some of your doctor's offices may still have them, but most of your hospitals have long gone away from single-phase generators. So 3/15, the easiest way to work this would be to reduce that to or not reduce it, but convert it to a decimal point. So that would be 3 divided by 15 would be your first step. 3 divided by 15, that would give you 0.2. So 0.2 into 20 would give you 100. So your MA station would be 100. Mass calculations, if a radiograph is made using using a 400 MA station 1/15 of a second, what is the mass? And that's just straight multiplication, 400 times 0.15. You can convert this to a decimal if you want to, 1 divided by 15, or you really don't have to. It would be the same as 400 over 1, which is 400 times 1 divided by 15. So fundamentally what you've got there is just 400 divided by 15. That would give you 26.6 mass. So what MA station could be used with 1/5 of a second to produce 60 mass? So again, I would convert that to a decimal. That would be the first thing that I would do. So it would be 60 divided by 2, 0.2 is 300. So what time is needed to produce 60 mass using 400 MA stations? So again, you're going to have 60 divided by 40, but we'll want to convert that to a fraction. So we've got 60 divided by 40, which is 0.15, and then to convert it to a fraction, we've got 0.15 is the same as saying 50 or 15/100ths. So that's an improper fraction. And it's an improper fraction because you can reduce that to a lower number. Both of these are divisible by 5, so if you divide 15 by 5, you get 3. If you divide 100 by 5, you get 20. So 3/20ths is a proper fraction, as opposed to 15/100ths is not. So if you have your textbook, you want to look at page 60, and some of the problems on here we'll want to take a look at. So on page 60, number 2, for example, you have 600 MA at 1/30th of a second, and the question is, what is your mass value there? So fundamentally, again, what you would do is multiply 60 by 1/30th. So it would be essentially 60 divided by 30, and you should have 20 mass. And then if you look at number 4, you have 200 MA times 3/10 of a second. Now what you would do is multiply the 200 by 3 and then divide that by 10. And what you would have is 600 divided by 10, and that would give you 60 mass. And finally, at the bottom, down close to the bottom, number 8, you've got 100 MA at 3/20ths of a second. 3/20ths of a second, you would divide 3 by 20, and that will give you 0.15. 0.15 times 100, you would have 15 mass. And again, we're going to increase by percentages. Remember, there's a difference between percentage of and increase by. In whenever you increase by, largely what you're going to have is a number larger than your original number. So if we increase 100 by 15%, you have to add that 100 back in. So you've got more than your whole. Your whole in this case is 100. You increase by 15%, so what you've got is 115%. And whenever you reduce by a percentage, it's just almost a straight subtraction. Reduce 100 by 15%. If it's straight subtraction, if our original value is 100, it gets a little more complicated when you get off that 100. But if you reduce 100 by 15%, then you're subtracting 15% from 100. So if you reduce 100 mass by 15%, what you would have is 85. So just mathematically running through those things that we just looked at, 100 times 0.15 would be 15 mass. You add the original value of 100 back in. So you got 100 mass, original mass plus 15 mass, you have 115 mass. And reduction by percentage is just the opposite of that. If you have a value other than 100, this is how you would work it out. You would multiply that value by 0.15 in this case because you're reducing by 15%. 100 times 0.15, that gave you 15 mass. And if you're reducing 100 mass by 15%, you subtract that 15 mass from the original value. So now your value is 85 mass. So when the percentage is over 100%, what we have is more than a whole, or we increased by a percentage. So it would involve increases only. So it's not to be confused with 100% of a number. Remember, 100% of something is that something. So 100% of 10 is 10. If we increase 100 mass by 100%, then we have an increase, so it's going to be bigger than that. It's going to be greater than what we had originally. 100% of something is that something. So what we've got is the original mass plus the original mass. So what we're going to have is 200% is what our mass value is. So it's twice of what it originally was. Now, it's not a 200% increase. That's still only a 100% increase. If it was a 200% increase, what that would be is 200% plus 100%. So a 200% increase would be 300 mass. But in this case, what we have is a 100% increase, which doubles the mass. So increased density 100% by using mass would be just what we were talking about. So the original mass value was 100. Increased density by 100% just using the mass, and what you're going to have is 100 times 2, which is 200 mass. Or you can work it out by finding the percentage of and then adding the original. So what that would be is 100 times 1.0, because that is your whole, and that is 100 mass. So 100 plus 100 is 200. But again, if we increase by 200%, then what we've got is something totally different. So you can work that out in one of two ways as well. You can mentally realize that the original one added to the 200% increase gives you essentially a mass value that would be 300% of what it originally was. So you could just say, well, 300% is 3. So 100 mass times 3 gives you 300 mass. Or if you are a little OCD and you want to take it step by step, that's fine. 100 mass times, this is your percentage increase. So 200% is 2.0. So 100 mass times 2.0 gives you 200 mass, but this is the step you can't forget to take. Add the original mass value back in because we're increasing by 200%. So you have to add that original mass value back in to get the 300 mass. So this is where we're going to spend most of the semester, is in contrast, density, visibility factors, geometric factors, and we're going to really hit it pretty hard all semester long. So contrast is just difference. So if you have something where you've got a lot of difference in contrast levels, what that means is you go from black to white very quick. So what you've got there is short scale contrast. You've got a contrast that goes from very few shades of gray, or goes from black to white and very few shades of gray. So it's short scale. Now, if you have your Bouchon, if you look on page 181, you see an image, figure 10-35, and it shows a lot of different shades of gray, a lot of different step wedge scales of grayscale. So short scale contrast will be what you're seeing on the left-hand side. I'm looking at my book, and I can only differentiate between about 5 different gray levels there. So short scale contrast means you go from the lightest coloration you can get to the darkest coloration you can get in just a few steps. So that's short scale contrast. As opposed to long scale contrast would be on the far right hand end. And you can count far more shades of gray on the right hand end than what you can on the left hand of that same graphic. So long scale contrast means that those gray levels are spread out over a broader range or a broader area. Where it gets confusing is whenever you apply that to high contrast and low contrast. So short scale means high contrast, and long scale means low contrast. And latitude you can kind of associate with grayscale. Long latitude, or an image that demonstrates a lot of latitude, would be long scale, low contrast. So what technical factor controls it? And when you're reading test questions from here on out, make sure that you're understanding what the question is asking you. If it's asking about technical factor, that's not computer algorithm. That's your technical factor. That's your KVP, your MA, and your time. So KVP is the technical factor that we say controls contrast. If we increase KVP, what we get is more penetration. So looking again at that graphic on page 181, the numbers at the bottom of each one of those step wedges represents the KVP that image was supposedly shot with. So if we increase KVP, what we do is we take those grayscales and we spread them out. So with the increased KVP, we get a decrease in contrast, we get an increase in latitude, and we get a longer grayscale. So the grayscale lengthens, the contrast narrows. We get long scale contrast, we get low contrast. So we don't really narrow the scale of contrast. That would be high contrast. We call that low contrast whenever we have a lot of shades of gray. So if we decrease KVP, then we get what we see on the left-hand side of that graphic, and that is that we don't penetrate nearly as many of these steps, and where we do penetrate, you can't really differentiate between the densities between them. So as we decrease KVP, our grayscale gets short. So we get short grayscale, we get a high contrast, we get low latitude. So other things can influence contrast. Again, the technical factor that we say controls the contrast is your KVP. But there are other things that can influence it as well. If you change from single phase to a high frequency generator, then with a high frequency, what you get is a higher average beam energy, which is kind of like KVP, but it's not completely like KVP. The average beam energy just means that more of the X-ray photons that you create will be more likely to penetrate through the patient. So you get a higher average, you get more penetration through the patient. It kind of works in the same ways as KVP, even though your peak energy doesn't go up. Likewise, whenever you change your filtration, which you're never going to do, then what you're left with is a more penetrating X-ray beam. And with more penetration, more of the photons, if you adjust your mass, more of the photons that reach the image receptor or strike the patient are more likely to penetrate through the patient and reach the image receptor. And what you wind up with is a longer grayscale, just like if you increase KVP. The primary difference there is your peak energy does not go up. Average energy goes up. And finally, grid use works in the opposite direction. As you change grid ratio, then you can affect a change in contrast. If you go from a low ratio grid to a high ratio grid, your contrast goes up because you remove some of the scatter radiation that would otherwise strike the image receptor. So the question, does high contrast carry more or less potential information? It really carries less potential information. You can get such a high contrast level that you can miss a diagnosis. If you're taking an x-ray of a patient's chest and you've got so much contrast that you can't see a tumor behind the rib, then you're going to miss a diagnosis. So where high contrast is very pleasing to our eye, it looks good, it's not always the best for diagnosis. So if you look on page 84 at the two skull phantom images, what you see is you got to look at it relatively closely to pick up what it is that they're trying to show you. But I think that the images that they're showing here utilize the 15% rule to try to maintain density while changing the grayscale. So the image on top, you've got 70 kVp, and if you look at where the dark areas and light areas kind of come together, you can kind of see some very stark differences, especially in suture lines. And then if you look down at the bottom image at 81 kVp, you see it's a little bit more gray, and you may have to look at it back and forth a couple of times in order to pick this up. But you can see a difference between the two images. Now, if you look coming out of that clip that's holding the bottom portion of the skull to the parietal bones, you can see what looks like little lines coming out of the top on the image on the bottom with 80 kVp. And those are just almost completely blend into the increased density, the darker darks in the image at 70 kVp. So you picked up a little bit more information in the bottom image compared to the top image. You can also look kind of down into the petrous ridges area, in the mastoid area. And again, the decrease in contrast is actually giving us more information on the bottom image. So we kind of have a terminology thing that we have to pay attention to whenever we're talking about increases in KVP. Sometimes we want to increase KVP and maintain the same exposure. Sometimes we want to increase KVP and increase exposure. Sometimes we want to increase KVP and decrease exposure. So at the same time, sometimes we want to decrease KVP and maintain the same exposure. Sometimes we want to decrease KVP, decrease the exposure. Sometimes we want to decrease KVP and increase the exposure. So make sure you pay attention to what your question is asking you. But a 15% change in KVP changes the exposure in the same direction by a factor of 2. What I mean by that is if you increase your KVP and that's the only thing you do, you increase your KVP by 15%, then what that's going to do is it's not only going to do everything that we talked about over here, which is to change your grayscale. You increase KVP and you get a longer grayscale and wider latitude and lower contrast. And then at the same time, if that's the only thing that you do, then the exposure or the density increases by a factor of 2 as well. So a 15% change in KVP is equivalent to a 2 times change in mass, a doubling of the mass. If you increase your KVP by 15%, it not only does all that stuff to contrast, but it also doubles your exposure as if you changed your mass by a factor of 2. So if we want a change in exposure with no change in contrast, then we don't want to use KVP. If we want no effect on contrast at all, then our technical factor to change would be our mass. So if you want to change exposure and contrast, then you would change your KVP alone. So if you needed to increase your exposure, your index number indicated that you were underexposed and you needed to increase your exposure, and at the same time you needed to change your contrast, then your factor of choice is KVP. So if you needed a longer scale contrast and to increase in exposure, then you would increase your KVP, and that's the only thing that you would change. So if you want to change your contrast with no change in exposure, then what you're going to have to do is you're going to have to do two things. You're going to have to change your KVP, but you're also going to have to change your mass. All right, so we've got a change in contrast, so we're going to have to increase or decrease our KVP. If we increase our KVP by 15% and we want no change in exposure, then we have to cut our mass back. And since a 15% increase in KVP doubles the exposure, and the exposure we equate to mass, then if we increase our KVP by 15%, then we have to cut our mass in half. So if we need a decrease in contrast, we need a longer grayscale and more latitude, we would increase our KVP by 15% and reduce our mass. That is your 15% rule. If you needed a shorter scale of contrast and less latitude, then what we would do is we would decrease our KVP by 15% and double our mass if we wanted to have no change in exposure at all. So mass and KVP for exposure, that is your density or your index number. Using mass only, how much of a change do you need to make to see a minimum difference? That would be a 20%, or I'm sorry, 30% change in mass would show you just a minimal difference. Now, realistically, you're not going to see that on your reader. That really applied to screens and films. So if I shot an image at 100 mass at any KVP, I shot a second one at 130 mass at the same KVP, really, I wouldn't see that much of a difference at all. I might barely see a little bit of a difference. So what we always said was that if you really needed to re-expose a patient, then what you needed to change, if the change was for repeat, what you needed to change was your mass by a factor of 2. So if you were underexposed, you would increase your mass by a factor of 2. So if you used 100 mass and you needed a repeat, then you needed 200 mass. If you shot with 100 mass and you were overexposed and you needed a repeat, then you needed to cut your mass in half. So you divide by 2 and you'd use 50 mass. So in the same way, you can use a minimum amount of KVP to affect a change. And the easiest way to remember this, I think, is that a 30% change in mass gives you a noticeable difference. A 15% change in KVP gives you a doubling of the exposure. So it's equivalent to doubling the mass. So if a 15% change equals a doubling and a 30% change equals noticeable difference, then a 30% change of that 15% KVP is going to give us a noticeable change. So 30% is roughly 1/3. So 1/3 of what you use to double the density with, or double the exposure with KVP, is what you would need to make a minimum difference. So 1/3 of 15% would be a 5% change. A 5% change in KVP is going to give you a noticeable difference. But if it's worth repeating, again, it's worth doubling the exposure. So your change using KVP, if you were to need to repeat an image because your index number indicated that you were too low, then it was probably worth changing your KVP by a factor of 15%. So mass and KVP for exposure, again, we've got using mass, increase the exposure by percentage using mass, decrease by percentage using mass, double exposure using mass, half the exposure using mass. So increase the exposure by percentage using mass, we kind of walked through that. You would just multiply by the amount of increase that you desired and add the original mass back in. So if you increase by 30%, you had 100 mass to begin with, that would be 100 times 0.3 plus 100 to give you 130 mass. Doubling the exposure using mass is just multiplication, multiply by 2. Half the exposure using mass would be division, so it would be divided by 2. So using KVP, a 30% increase in exposure with KVP would give you a noticeable difference. Again, that's your 1/3. And doubling the exposure using KVP would be changed by 15%, increasing your KVP by 15%. So manipulation of both contrast and exposure. You got to read the question. If your question is asking you to increase contrast, take it one step at a time. Increase contrast, stop. What causes an increase in contrast using your technical factors? Well, KVP controls contrast. I need to increase contrast. So I'm moving in that graphic again on page 181 of Buchung towards the left-hand side. So what's your technique on the left-hand side that gave you higher contrast? So decrease in KVP gave me an increase in contrast. So I need to decrease KVP, but I need to maintain exposure. So 15% decrease in KVP, double your mass. If I need to increase contrast and decrease exposure, again, whenever we change our KVP, then we're going to get a change in exposure as well. So if I need to increase contrast, again, we increase contrast, we go to lower KVP. That gives us an increase in contrast. Well, what we looked at before is if we increase KVP and we don't do anything with mass, that increases exposure. So if we increase contrast and decrease exposure, then we're going to decrease KVP and we're going to leave mass completely alone. If we decrease contrast and increase exposure, then we're going, again, decrease contrast means more shades of gray, longer grayscale, so we're going more towards high KVP. So if we decrease contrast, we're increasing KVP, and that's automatically, if we don't do anything with our mass, we're going to increase our exposure. So if we decrease contrast and decrease exposure, then again, decrease contrast, KVP. Decrease contrast, high KVP. So we're going to increase our contrast, but if we increase our contrast and decrease exposure, what I'm going to have to do is increase my contrast, double my increase KVP, cut our mass value in half, and then I'm going to have to reduce it past that to decrease the exposure. So what I may have to do is increase KVP, cut the mass in half, cut the mass in half a second time. So again, what do we need to change if we want to increase contrast? Stop there. Increase contrast, that means shorter grayscale, that means lower KVP. So increase contrast, but maintain exposure. So we're going to decrease KVP, increase mass. What do we need to do if we want to increase contrast? Again, increase contrast, reduce KVP, and decrease exposure. We're going to decrease KVP and leave mass alone. What do we need to do if we want to decrease contrast and increase exposure? Decrease contrast, increase KVP, but we want to increase exposure, we want to leave mass alone. What do we need to do if we want to decrease contrast, which is increase KVP, and increase exposure? Okay, so I found another error here. This would be decrease exposure. Then what I would have to do is increase my KVP and reduce my mass twice. So what we have not talked about is what if you want to increase your contrast and increase your exposure? If you want to increase your contrast, you have to reduce your KVP. So your KVP would reduce by 15%. You double your mass if you wanted to maintain your exposure. That only gets you to maintain the exposure. So what you would have to do is double your mass again if you wanted to increase contrast and increase exposure. So this just kind of runs through what we just talked about, kind of a cheat sheet. Increase contrast and maintain exposure. What we're going to do, increase contrast, reduce KVP, increase mass by a factor of 2 because we're maintaining the exposure. If we want to increase contrast and increase exposure by a factor of 2, it gets a little bit more dicey. So we're going to decrease KVP, that gives us an increased contrast, but we want to increase exposure by 2, then we're going to decrease KVP by 15% and increase mass. That's got to be more than 2 because we doubled our exposure. In doubling our exposure, what we have to do is we have to increase our mass by a factor of 2 and then again increase that by another factor of 2. If we want to increase contrast and decrease exposure by half, then we decrease KVP by 15% because again we're increasing contrast. We'll leave the mass alone. So go in an opposite direction. If we want to decrease contrast and maintain exposure, then we're going to increase KVP by 15%. Because we're maintaining exposure, we want to cut the mass in half. So we want to reduce mass by 50%, divided by 2. If we want to decrease contrast and increase density or exposure, then we're going to increase our KVP by 15%. And that's automatically going to give us a doubling of our exposure or our density, so to speak. And that's going to take care of itself. We don't need to change the mass at all. So if we need to increase contrast and decrease density, you know what, we're going to change this one. We're going to say if we're going to decrease contrast and decrease density, then what we need to do is increase KVP by 15%. And then what we're going to do is, let's say we want to decrease in contrast and a change in density by a factor of 2. So what we're going to do is we're going to increase KVP and we're going to have the mass twice. And what that's going to do is, with the increase in KVP, we're going to reduce the contrast, but we want a reduction in exposure or density. So if we cut the mass in half once, then that gives us our original exposure, but we want to decrease the exposure, so we're going to have to decrease it a second time. So working through some numbers. What if we wanted to increase contrast? Stop there. Increase contrast means that we're going to do what with KVP? And then proceed on. And increase exposure by a factor of 30%. So original technique is 100 kVp, 10 mass, and what we want is more contrast and 30% increase in exposure. What would the new technique be? So what you would do is you'd take it incrementally. So if you wanted 100 kVp, your original technique was 100 kVp, 10 mass, you wanted more contrast, then you need to reduce that by 15%. So reducing that by 15% would automatically reduce your exposure, but you want to maintain your exposure. So let's take this incrementally. You want to maintain your exposure. So what you would do is decrease that by 15%, maintain your exposure. So if you reduce that by 15%, you'd have to double that. So that gets you to step one. Step two would be to reduce your, increase your exposure by 30%. So 100 kVp down to 85 kVp. This would increase to 20 mass, and then you would increase from that by 30%. So take things incrementally. So reduce kVp by 15%, then double mass, and then add the 30% increase. So it'd be 100 kVp. That would give you, 100 kVp 10 mass technique would require more contrast and 30% increase in exposure. So we're going to reduce by 15%. That gives us 85 mass. If we did nothing else, we'd have an increase in contrast and a reduction in exposure. So we need to increase our mass by a factor of 2. So our new mass is 20 mass, but we're not done yet. We have to increase that 20 mass by 30%. So 20 times 0.3 would give us 6 plus 20, we have 26 mass. So our new technique is 85 kVp at 26 mass. So what this quiz is going to entail is that, and the test especially is going to entail are multiple steps. So what if you needed an increase in contrast, an increase in exposure, and a decrease in motion? So you're not really changing mass value here, but you're going to have to calculate something that would give you shorter motion. And what are the ways that you control motion? Good patient care, good instructions for the patient. But machine factors are the timer setting that you use. So your original technique in this scenario was 100 kVp, 100 MA at 0.1 second. So that gave you 10 mass. So you need less time due to motion, but you need more contrast and a 30% increase in exposure. So it starts identically to the last one. So you're going to decrease your kVp by 15%, double your mass, increase the mass then by 30%, and then you're going to make adjustments to your MA station. So take things incrementally, one step at a time. So you're going to double your MA station. You went from 100 to 200 MA station, and your mass now is going to be half of what it was before. Remember, we have two square laws. One is the inverse square law, and one is the direct square law. Remember when you use each one, what each one is used for. The inverse square law is the intensity of the radiation is inversely proportional to the square of the distance. So as you increase distance, your exposure goes down. So that's an inverse square law. Most of the time that we give you an inverse square law problem, what we're asking for is the exposure to the image receptor. How much of a change is it? Does a change in distance give you to the change in image receptor exposure, or dose to the patient? So most of the time it's going to be dose rate. The direct square law is technique compensation. So if you double the distance, I know some of y'all are probably still kind of locked into double the distance. You're going to you increase your distance by a factor of 2, then your dose is going to go down by a factor of 2, and that's not right. If you take a flashlight and you project it on a wall from 40 inches and you back up to 80 inches from the 40 inches, what you'll see is you get a doubling of the length and the width, which means that the light that you project is spread out over 4 times. So it's 2 squared. 2 times 2 is equal to 4. So the intensity changes by a factor of 4. So if you double your distance, your intensity decreases by a factor of 4. If you cut your distance in half, then your intensity increases by a factor of 4. So direct square law, again, is what we use whenever we're trying to calculate um, technique changes for changes in distance. So it's used to figure new mass rates with changes in distance. It's a density maintenance formula. So it's mass 1 over mass 2 is equal to d1 over d2, where distance is the d. So if you look, the difference between the two, really, since intensity is mass for our purposes, the difference really is the secondary side of the equation. And again, this is just a ratio equation. I could have written it like the quiz today. Some of y'all whiffed the quiz, and I could have written it like this, and you might have recognized it a little bit better. Let's see, I1 over is to I2 what D2 is to D1. That's really what threw you off on the quiz. It's really just ratio problem is all it inverse and direct square law questions are. So it's the intensity of radiation is inversely proportional to square of the distance. Double the distance, then we've got a factor of 4 change. Same thing happens with direct square law, only in exactly the opposite direction. So mass 1 over mass 2 is equal to d1 over d2. So doubling the distance, what we're going to need, because we've lost most of our intensity on each one of those 4 sections of where you shine the flashlight, double the distance, it spreads out over an area 4 times as large. So to get the same exposure to each one of those little portions, what you would have to do is increase, in the flashlight example, the amount of light by a factor of 4. In our circumstances, in our example for X-ray, double the distance, we're going to have 4 times the mass. So if you half the distance, you're going to have 1/4 the mass. So it changes from 40 to 72 inches, requires a change of 3.24, so roughly 3 1/4 is your conversion. So if you change from 40 inches to 72 inches, what you're going to need is 3.24 times the amount of mass. If you go from 72 inches to 40 inches, you're going to need 3.24 the amount of mass. So if the radiation dose is 40 inches is 20 MR, what will the dose be at 36 inches? So you got to ask yourself, what problem am I working there? It's asking for dose. So that's going to be the inverse square law. So if radiation dose of 40 inches is 20, what will the dose be at 36? And the first thing you need to ask yourself is my dose going to increase or is it going to decrease? Well, since we're decreasing distance and we're looking for dose, then the closer you get to the source of the radiation, the more dose you're going to receive. So it's going to be more than 20. So if you work the problem and you get something smaller than 20, you know you did something wrong. You probably used the wrong formula. So will the dose increase or decrease? Well, it's going to increase. So 20 over x is equal to 36 over 40 squared. You square that side, you get, and you reduce it down, you would have 81 over 100. Cross multiply, you're going to have 25 MR. So that 4-inch change, it's only 4-inch change, increased your radiation dose really by, what would that be, 25%. So the takeaway from this is not just how to work a inverse square law question, and it's not really just when to use inverse square law versus direct square law. It's really kind of a move away from the source. So where most of your radiation dose comes from is scatter radiation from the patient. So that 4 inches changed that dose by 25%. So if you can step back a foot, it's going to reduce it significantly, even more than that. So again, stand as far away from the patient as possible. If you have to be in on a fluoro case, stand back as far as practical. You certainly don't want to be all the way up against the wall when the radiologist is asking for barium, but there's no reason for you to be hugging the table.